In the early 1900s, American children had a life expectancy of only 44 years. During this part of the century, most people would spend their entire life in a 50-mile radius and might only travel 1,500 miles in their lifetime. People would awake to the sunrise or a hand-wound alarm clock. There was no radio or television for the morning news, no faucet with running water, and cooking breakfast meant using firewood to warm up the stove. What engineering advancements of the past 100 years changed our lives so significantly? On this show, we'll see the defeat of threats as vast as nationwide illness, natural disasters, and hostile enemies. We'll take a look at the significant contributions that scores of engineers have made to make life easier, safer, and better, as targeted by the American Council of Engineering Companies. We'll see ingenuity, inventions, and visionaries engineering a century of change. In the early 1900s, most Americans had no running water, used outhouses, and the third leading cause of death was directly caused by unsafe drinking water. The need for safe drinking water was exacerbated as the United States swelled with immigrants. New Americans streamed in through Ellis Island at 100 per hour, and the U.S. was populated by 76 million people and growing rapidly.
If you look at what life was like in the 1900s and before, purified water was non-existent. My grandmother, in fact, was born in 1894, and I remember talking to her about her life as a young child. Dysentery, typhoid, cholera were very common diseases, and she grew up deathly afraid of those type of diseases.
Typhoid fever was a scourge in America. It alone was causing deaths annually of more than 150 people per 100,000 in population, including Wilbur Wright, who died at the age of 45 in 1912.
A lot of folks thought that water merely purified itself, running through a stream such as this. As civilizations grew up, of course, they grew up around water courses, and we used typically the water streams as cesspools, and it took away our wastes and our sewage. We didn't really understand what was going on with microorganisms and pathogens and what damage we were doing to the downstream folks who were drinking this water.
All this changed when a little-known engineer named Abel Wohlman developed a new technique for disinfecting water with chlorine. But even with resistance from taxpayers as to the cost, water treatment systems flourished.
In the 1920s and 30s, virtually every community in the United States were to build and install their own water treatment units and processes such that their communities could enjoy safe water. By 1930, waterborne disease had virtually disappeared in the United States.
In only a few short years, the nation's water supply was changed from a deadly to life-giving force and helped fortify America for the next changes to come. Although the pursuit of clean water made great strides at the beginning of the century, controlling water was not an easy task. And in many areas, rural and urban, a devastating yearly ritual took place: floods. In the spring, floods would wipe out numerous areas, sometimes yearly, while in late summer, droughts and shortages of water would plague U.S. cities, particularly in the West. A network of river dams needed to be put into place if the nation was to grow.
The dams were then installed for flood control by the Corps of Engineers back in the 30s to prevent massive flood destruction along the major rivers in the United States.
Apart from the danger of floods, water needed to be moved to numerous locations for struggling farmers and settlers. The nation's rivers were not navigable, and upstart communities needed power to grow. Although hundreds of dams across the country have allowed arid regions to flourish with farms, made navigation possible from the Gulf of Mexico to the Atlantic Ocean, and supplied hydroelectric power throughout the country, one dam set the standard by which all others are measured: Hoover Dam. Twice as tall as the Statue of Liberty, it remade the West. Built during the Great Depression, a makeshift town of 5,000 was constructed to complete it. The Hoover Dam provided work and staggering benefits. It tamed the raging Colorado River, supplying water and irrigation to bone-dry areas in the west and southwest. Its hydroelectric generators supply electric power to people in Arizona, Nevada, and Southern California, and it created Lake Mead, a reservoir that would become the largest global man-made lake. Not only did Hoover Dam supply water and power to the West, but it also gave hope to the country. Because the dam was built with the blood, sweat, and tears of those thrown out of work by the Depression. It demonstrated our ability to overcome adversity and once again achieve grand goals. At the start of the 20th century, electric power was young, but growing rapidly. Thomas Edison's work had led to the first direct current commercial power plant in 1882. DC power stations could only distribute electricity a short distance. The work of engineer Nikola Tesla led to the commercialization of alternating current, which enabled transmission of high-voltage power over large distances. But even with most of the population of the United States living in rural areas, power was still focused on cities. Without electricity, life on the farm was tough. No light, no running water, no refrigeration, and rainfall was the only chance to get water to the crops.
You'd go west out of Omaha, cross the Platte River, and from there on the country just sort of looked like a desert. You'd see farm after farm deserted. Without electricity, a farmer had to live in a dark house. He'd have to pump his water by hand.
As the Great Depression hit, only 10% of the nation's 7 million farms had electricity. But in 1932, FDR is elected president, and by 1936 establishes the Rural Electric Administration. A government study given to REA administrator and engineer Morris L. Cook said that a lack of electricity on farms is a social problem, not an economic problem. He disagreed. To make electricity affordable, engineers instituted innovations that included standardized distribution lines, and the REA provided loans to municipalities that met the criteria.
In order for a county to apply for an REA loan, you had to drive around the county and locate the farms with an X, and there had to be at least 2 farms to the mile to get enough usage out of the electricity to pay for it and make it self-supporting.
This blueprint, now used worldwide for electrification, changed America's ability to irrigate crops. And as for the report that said it was not an economic problem, today agriculture accounts for 14% of the U.S. economy and $50 billion in exports. One of the most life-changing engineering achievements of the century. In the early part of the 20th century, automobiles were the first in a parade of advancements. Unfortunately, roads still used for horse traffic were not as advanced. Streets were predominantly made of dirt, brick, and even cedar blocks that made the new craze of driving a somewhat dubious endeavor.
Very few of the rural roads were paved, and when you did get a real rain, you're up to your hubcaps in mud.
In 1919, a young soldier named Dwight Eisenhower decided to join a motor convoy across the United States. An endless series of mechanical difficulties, vehicles stuck in mud, roads as slippery as ice made a lasting impression on the future president. But in 1949, a surprise announcement by Harry Truman shocked Americans. Years ahead of predictions, the Soviet Union successfully tested an atomic bomb. The government felt there was a need for the population to escape quickly in case of a nuclear attack. It also wanted to be prepared to move troops and missiles at a moment's notice. President Eisenhower worked feverishly to push through at all costs a way to provide money to create highways linking the entire country in a master plan using federal standards for conformity. But how easy would it be for engineers to create 40,000 miles of highways for an entire nation using the same federal standards through 48 states of differing terrain? Hundreds of unique engineering designs had to accommodate deserts, bodies of water, mountainous areas, and other topographical phenomena, and still achieve the same result. Considered by some as the greatest public works project in the history of the world, it also lived up to Eisenhower's hopes given in a speech prior to its inception. Together, the united forces of our communication and transportation systems are dynamic elements in the very name we bear, United States. Without them, we would be a mere alliance of many separate parts. Like the interstate highway system, bridges have also been a major factor in the mobility and economic improvements of countries worldwide throughout history. In 1931, the George Washington Bridge was part of an American trend to build the biggest of everything. The bridge's 3,500-foot center span was almost twice as long as the largest existing bridges at that time. But more recently, a new type of bridge has been pioneered, one that would eventually change the way bridges in the U.S. would be built for the rest of the century and beyond. It's called a precast concrete segmental bridge, now the method of choice for many transportation projects and used to build the Sunshine Skyway Bridge, the Glenn L. Jackson Memorial Bridge, and the 7-Mile Bridge in the Florida Keys.
Precast concrete segmental bridge technology brought about a host of benefits to bridges, including economy, quick construction, and exceptional beauty. They're a bridge type that is adaptable to any bridge site. And you precast pieces off-site, bring them to the site, and erect them quickly.
In bridge building, much of the descriptive language used to describe bridge projects are words like tallest, longest, widest. But then along comes a project that adds a new term to the lexicon: smartest.
The Natchez Trace Parkway arches in Tennessee that we accomplished for the National Park Service is a precast concrete segmental bridge with a 582-foot arch, really a first in America. And what we did here was to eliminate the spandrels that you would normally see in an arch to create more openness.
Maybe the most shocking single piece of information about this bridge is that when completed in 1994, it cost only a little over $11 million. This type of engineered bridge, which is simple yet elegant and cost-effective yet functional, is the precursor of bridge projects to come. Space travel and skyscrapers are the most publicized of engineering achievements. But one underappreciated engineering milestone made those and other advancements possible while changing the lives of millions of people during the 1900s. Air conditioning.
Before air conditioning, there was always an effort to get comfort and have some cooling in the summer. And most of it was dependent upon the utilization of ice. And we took the ice by cutting it in the winter out of the lake and storing it for the summer. They'd stack up ice in racks and blow air across it.
It took the pioneering genius of engineer Willis Carrier to work out the basic principles of cooling and humidity control. In 1911, Carrier presented his paper, Rational Psychometric Formula, to the American Society of Mechanical Engineers that formed the basis of air conditioning.
Once air conditioning was developed, the benefits of it became immediately known, and there was a big rash of wanting to use air conditioning.
This quiet yet amazingly important development of AC not only provides comfort for 70% of U.S. households, but made possible numerous advancements. microcomputers, space travel, skyscrapers, food and biomedical preservation, and others. It is one of the most taken for granted, yet one of the coolest advancements of the 20th century. As the population of the United States shifted from a rural to a predominantly urban demographic, the nation's lifestyle changed, and with it, so did cities. Even with recent tragic events, nothing says America to the rest of the world than the huge buildings that decorate our skylines.
We've always reached for the sky as a people, even in antiquity with monuments and towers. In the early 1900s, the tallest building that we built would be on the order of 10 stories, and it was a brick and mortar building. And then with a new material, steel, we began to grow.
With steel as a new component, the race for the tallest building began. The Empire State Building became the model for the industry. At 1,250 feet, it stood as the world's tallest building between 1931 and 1972. The workforce averaged 2,500 men. But contrary to folklore of the time that skyscrapers cost a life for every floor, there were only 5 deaths during construction. Built with Great Depression dollars, it cost only $24.7 million. But at first, hard times left the structure with so few tenants that it was referred to as the Empty State Building. After 41 years, it was finally surpassed in height by the World Trade Center towers and John Hancock Building. But how will recent events affect skyscrapers?
With the attack on the World Trade Center, we have introduced into our design process another design parameter. You could put the way we design buildings as, let's define the threat. If we can define the threat, we can design against the threat. So to date, for non-military buildings, installations, the threats have been natural, wind and earthquake, and furniture and people. Now we have another one. We have another one.
Many engineering projects that revolutionized daily life usually ran hand in hand with advances in materials. Throughout the century, chemical engineers learned new methods to analyze and refine chemical processes to maximize their performance.
Before 1900, you pretty much had to go and get natural materials if you wanted to make something, such as stone or animal fibers. You basically had to find an animal and see which part of it you could make something out of it. And what the chemists did is really to figure out how things are put together on a molecular level, rearrange their atoms, make new molecules with new properties. And with those discoveries, the chemical engineer would come in and take that to an industrial process where they could now scale it up so that it would be something that everybody could use.
But with all the accomplishments of chemical engineers and material inventors, including the development of plastic, which now exceeds steel production by volume and mass, one particular event sums up the value of chemical engineering in the 20th century.
One event which really exemplifies what a chemical engineer can do is the story of how in World War I, Germany was cut off by the British from rubber supplies. And so what that meant was they couldn't drive their cars, the soldiers didn't have boots.
Then in the opening days of World War II, with several fascist armies threatening to take over the world, Japan rapidly captured rubber-producing lands in the Malay Peninsula and East Indies, depriving America of 90% of its natural rubber sources. Suddenly, America found itself in the same undesirable position that had confronted Germany 40 years before.
What happened was then the government and industry got together to try to put together a system to make synthetic rubber, and that's where the chemical engineers contributed. And by the end of the war, 4 years later, they were making 100 times the amount of synthetic rubber that they were making compared to the beginning of the war.
Unlike early man, who used a few tools over thousands of years as lifestyles evolved slowly, in contrast, 20th century man developed thousands of tools in a few years, and the way we live has changed proportionally. In 1955, an early high-speed commercial computer used vacuum tubes, weighed 3 tons, consumed 50 kilowatts of power, and cost $200,000. It could perform 50 operations per second, a feat unheard of for its time. Today, a laptop computer weighs 5 pounds, can perform millions of operations per second, and costs only $1,000.
The benchmark in time where you could really start to see the miniaturization of all our electronics happen with the invention of the transistor.
Invented in 1947 by Bell Labs engineers and scientists John Bardeen, Walter Brattain, and William Shockley, the transistor replaced bulky vacuum tubes. By the early 1950s, the transistor had captured the world's imagination with the transistorized radio, the fastest-selling retail object of the time. Soon, millions of transistors could be placed on a tiny silicon chip in integrated circuits called microprocessors.
As this miniaturization continued and the power requirements dropped and the size of a computer chip dropped and the number of transistors we could put on a piece of silicone increased, we were able to come out with a smaller computer, starting with an Altair.
Now those massive units that once filled a room and were used only for number crunching could be on your desktop, in automobiles, airplanes, and thousands of other products. The invention of the transistor helped miniaturize, in the last half of the century, all of the major inventions of the first half of the century. It was this single event that led to the accessibility of the personal computer, the growth of the internet, and helped launch America into space. Long before anyone ever thought it was possible to go into outer space or to the moon, in 1898, a young boy reads War of the Worlds and decides to make rocketry his life's work. His name was Robert H. Goddard, and he would become the father of modern rocketry. In 1919, financing most of his experiments with his teacher's salary and a small grant from the Smithsonian Institute resulted in a small booklet, less than 70 pages, called A Method of Reaching Extreme Altitudes. A short sentence mentioning the possibility of sending a multi-stage rocket to the moon was included. The New York Times pounced on the sentence with an article which accused him of talking nonsense. It stated, "Goddard does not know the relation of Isaac Newton's action to reaction against the vacuum of space. He seems to only lack the knowledge ladled out daily in high schools." From that point forward, Goddard kept quiet and kept going. Test after test improved Goddard's theories, and 40 years later, with the space race underway, Goddard's rocket engines formed the backbone of the space program.
Liftoff. We have a liftoff.
Rocket propulsion results in a violent explosion that produces very hot waste gases. These gases are forced at high speeds out of the rocket nozzle. A second stage explosion then fires to propel the payload to its correct orbit. From one small boy's dream, the launch and return of spacecraft from Apollo to the shuttle is one of the monumental engineering triumphs in all of human history and has spawned more than 60,000 products that have had a direct impact on the general public. On July 20th, 1969, humans watched a man walk on the moon on their television set, at the same time looking up to see the moon. After the lunar landing, the New York Times printed the following retraction 50 years later. Further investigation has confirmed the findings of Isaac Newton in the 17th century, and it is now definitely established that a rocket can function in a vacuum. The Times regrets the error. All the engineering advancements of the 20th century were problems corrected with a unique solution. What might we expect in the near future from engineers that might change lives for the better?
The technology that we have available today, engineers to make the world, because that's what we do, we make the world, it's more a matter of choosing where we want to put our effort. Do we want to put our effort in a tall building, or do we want to put our effort in a new energy material? Where do we want to put it? what's important to us.
The people looking into the future from 1900 could have had no idea of the rapidity of changes that would mark the 20th century. But through the years, engineering ingenuity has helped mold the world into a new place, with safer conditions and a better environment, which were contributing factors to this man with a life expectancy of only 44 years, still going strong at 97, with more to come. What changes will today's young children experience? There's no way to know for sure. But if the engineering achievements of the 20th century are any indication of the future, they could be in for quite a century.